The last operation that we need to undertake on our red-black tree is to remove a node. Removal of a node in a red-black tree is the most complicated operation for our tree data structure, and that's because we have to maintain all of our red-black properties in a tree that has a lot of structure already in it. So the process of removing a node from a red-black tree involves a lot of different cases that we're going to consider in turn. So the general process that you're going to follow is when you want to remove an element from your red-black tree, the first thing that you have to do is you have to find it. So you find it using search, just like you would do in any binary search tree, and eventually you will find the node. Well, if you don't find the node that you want to remove, then you don't have any work to do. But if you do find a node that you need to remove, then what we need to do is we need to account for the colors, and we need to restructure the tree so that the data continues to follow our binary search tree constraints and follows our red-black tree constraints. So the way that we're going to do that is before we remove a particular node, we're first going to turn it red. And by turning it red, we're going to have to fix any double black or double red violations. And that's going to, we'll describe that in a second. All right, so when we find the node we want to remove, we remove it the way we remove something in a regular binary search tree. And if you recall, what that means is it means we have a node that we want to remove, and we have to search down the left-hand side, or we have to search down the greater side, so the right-hand side, to find the smallest element in our right-hand side. So the smallest element that's greater than our root node. When we find that element, we examine its color. If the color of the element is red, then there's no problem because we can just take the data that's there and move it into the node that's about to be removed. By doing that, we've removed one red node, but that doesn't introduce any double reds, and it doesn't change the exit cost at all. On the other hand, if the node that we want to remove is black and has one child, then we can do a basic restructuring as shown here. We take the N1 data and we put it into the node that's about to be removed, and we repair this portion of the tree by shifting T1 and T2 to be children of N2, moving N2 up to the spot that N1 was removed from, and coloring N2 black. In this way, this little piece of the subtree has no double reds, and it has the same exit cost preserved, and it maintains the binary search tree. The difficult thing to do is if we want to remove a black leaf. And this is a difficult operation to undertake because removing a black leaf violates our equal exit cost rule. We're going to be taking away one of the toll booths in our tree as we move from the root down to the leaf. So as a result, we have to do a couple things. First of all, what we're going to do is we're going to turn it into a red node, and then we're going to go about repairing it. The way we're going to repair it is by taking that cost that used to be embodied in our black node and by shifting it up one so that the cost is preserved up above. So we have to find the exit cost, that we have to take that toll from the path from somewhere else. So if we have like gray nodes and we think about it abstractly, we're going to remove one of the nodes and we want to add a toll booth cost to our parent, and we want to remove it from the children. And depending on the situation that we're in, we might do that in different ways. For example, there are 6 possible configurations of a subtree in which we want to remove our black nodes. These are indicated here with the X's. We may have 2 trees with red parents, and then the X might be on the left or the right. And we might have 2 trees with black parents and 1 red child and 1 black child, and depending on which one we want to remove, it might be on the left or the right. And then finally, we might have children with all 3. If we are trying to bubble up the cost of removing our X node and remove from our parent node, the 2 trees on the left are easy to account for. All we have to do is remove the node that has an X, turn the parent into a black, increasing that cost by 1, and turn our sibling into a red, decreasing that by 1. The problem is if we end up trying to increase the cost of our parent node, which is black, or decreasing the cost of our sibling node, which is already red. That makes something a double black or a double red, meaning we need a black node to have twice the exit cost or a red node to have negative twice the cost. And so we can fix that with another transformation that's sort of a recipe. If we have a double black node like N4 and we have a negative red node like N2, we can do a rotation where we replace the root node with what was N3, keep N2 where it is, and move N4 down one. So it's sort of a rotation. And we modify the color so that we have 3 black nodes. And then we change N1 to red. In this way, we've preserved the exit cost of removing our nodes. We have maintained our binary search tree condition. We may have introduced a double red on the children of N1. And so we recursively need to go down and fix any double red problems that we've created with N1. That may, in turn, cause us to interact with the root node. We may have a different situation with double red and double black or double red. Because fixing a double red violation might also, by fixing our double red violation, we also fix our double black grandparent. So again, what we're doing is we're recursively looking at our N1 node from here, down here, and we're going to have to deal with that. And so we're going to transform our double red situation, where the middle layer there is N1 from our previous slide, and we rotate it around so we have 3 black nodes. Finally, if we end up with a double black node and it ends up at the root, we either do our straightforward repair, or if we end up with a double black node at our root, we can just replace it with a single black node. So this is, then that preserves the equal exit cost because we have just subtracted 1 from all paths. All right, so removal is pretty complicated, and the best way to go through it is to look at some examples. So I'm going to give you some animations that you can follow in very slow motion to try and understand the process by which you identify, first of all, when you remove a node, where in the binary search tree you look, and then how you change the colorings in order to replace that node that you're removing, and then how do you repair the tree as a result. We'll look at an animation to do that in a second. Of course, removal is very efficient as well. Overall, our red-black tree is very efficient. If we want to find an element, it is the best efficiency that we can hope for in a tree because it is a bushy tree, and so finding something only requires us to look at one path from the root to the leaf. We know that if we have n elements in our tree, the height of our tree is log n. So finding something is order log n. Adding an element also requires us to find the position in the tree, order log n, and then possibly do half h over 2 operations to bubble up the red over the top. So even if it took us 2h, overall, that's just a constant times log n. So adding an element is a log n operation. Finally, removing an element has the same kind of structure. We have to find the element to remove, that's log n, and then we have to do a repair structure, which is also taking care of repairs just along one path from the top to the bottom. And so at most, that's going to be something like 2 log n. We can get rid of that constant, and we see that all the operations on a red-black tree are log n. And because of the repair operations that we're doing, we never get into a degenerate situation, and we can use a red-black tree to create a very efficient representation of a tree set. Thank you for your attention.